Okay, everyone, I have another practice problem for us to look at together. This problem involves looking at an equation for the temperature of just a small little pool of water that's been left in a city street. We're going to model it with the polynomial function, t minus 3 cubed minus t squared plus t plus 27. And that is going to be the model for C of T, the temperature in Celsius, from 7 a.m. to 12 p.m. So we're just looking at a 5-hour time period, okay? We'll let T equals 0 be 7 p.m. So that's going to be T equals 0. So T equals 1 hour would be 8 a.m. Okay, our first question for this is during which hours is the temperature decreasing? So we know that a function will be decreasing whenever its derivative is negative. So that's exactly what we're going to do. We're going to take the derivative of this function. All right, so I will bring the 3 down in front here. Taking that 3 right there, putting it down in front, and this becomes 3 times t minus 3 squared. Now I just simply need to multiply by the derivative of the inside because of the chain rule. The derivative of t minus 3 is 1, so I could say times 1, but that's not going to change anything, so I'll just skip and move on to the next one. All right, and for the next term, I bring the 2 down. I have 2t to the first power, and then simply plus 1 for the t, and the derivative of 27 is 0. Okay, to make this easier to solve, I'm even going to go ahead and expand this here. So I will leave the 3 like so, and we'll expand this and get t squared minus 6t plus 9. Then we have minus 2t plus 1 still. Okay, so if I distribute this 3, I get 3t squared. Then 3 times a negative 6 is a minus 18, but I've still got another minus 2t over here, so I'm going to go ahead and combine those to a negative 20t. All right, and then I got 3 times 9 is 27, but plus 1 at the end makes that a 28. All right, so we're looking for critical numbers here so that we know when the derivative switches from increasing to decreasing or decreasing to increasing. There is no place where the derivative c prime of t is undefined, so we just need to solve it equal to 0. So I'm going to go ahead and do that. And hopefully this is indeed factorable. It's not unheard of for us to have to use the quadratic formula even on a non-calculator question. Well, let's see here. 3 times 4 is 12. No, 3 times 7 is 21. Let's see here, 12. All right, so here's what I'm going to do. I'm going to say 3 times 2. So I'm going to have a minus 2 here. And I'm going to have 3t minus 14. I think that's going to do it if I did my arithmetic correctly. Let me just do a quick check on that. So this times this would give me 3t squared. That's good. T times a negative 14t, that would be a negative 14t. And then that'd be a negative 6t. That makes a negative 20t. All right, that's good. And then negative 2 times negative 14 is a positive 28. Okay, so we are good to go. So I think you can see then our critical numbers are t equals 2. And t equals, we would have to divide 14 by 3. All right, so if I just go ahead and make a quick little number line here just to make this easier to do. Now 14 divided by 3, that's just a little bit more than 4. That's 4 1/3, I believe. 4 2/3 actually. So 14 divided by 3, and we'll put 2 over here. And what we're going to do is we're just going to make a little sign, a little bit of a number line just to evaluate the signs of C prime. Okay, so if I plug in a number in between 2 and 14 over 3, like 3, into C prime, and I can use the factored version of C prime. 3 minus 2 is a positive number. 3 times 3 is 9, minus 14 is a negative. That's going to be negative. Now over here, if I plug in a 0 in for t, I think you can see that it starts at a positive 28, so that's positive. And then over here, if I plug in something like a 5, I would get a positive times a positive. So as we would expect, since this is a parabola-shaped derivative that's opening upwards, it goes from positive down to negative and then back up to positive again. So we can actually finally answer the question that this is happening on the interval from 2 to 14/3 hours after 7 a.m. So we could be, even more real world sounding, because we could say from, 9 a.m. to now 14 over 3, as we said earlier, was that is 4 2/3 hours. So if I add 4 to 7, that's going to be 11 hours, and 2/3 is 11:40. Okay. All right, next. So during which time was the temperature increasing at an increasing rate? So we've seen questions where we're asked when is a function, when is it changing at an increasing rate? When is the slope changing at an increasing rate? Well, I'm going to ask this one a little bit differently, just to give us something else to think about. I want to know not just when the temperature is increasing, not just when the rate of change in the temperature is changing at an increasing rate, but I'm looking for increasing and increasing rate. So if we're thinking about acceleration, we're talking about a positive velocity, a positive acceleration. We want the temperature going up, and we want the rate of change in the temperature going up. Well, we already know that the temperature is going up from 0 to 2 and from 14/3 to the end of our interval, which is 12 p.m. So the question is, where on those two portions is the rate of change also increasing? So I'm going to repeat this procedure. I'm going to take the derivative, and I'll use the version that we have right here. I'm going to take the second derivative of that, giving me 6t minus 20. So this is the rate of change of the rate of change. And if this is a line, if we were to graph this, this would be just a kind of a diagonal line. It's going to start at negative 20, and it's going to have an x-intercept at 20 divided by 6, or 10/3. And that's, a little bit over 3. That's 3 1/3. So before 3 1/3 hour, the rate of change in the temperature is actually negative. Now we see that the rate of change of the rate of change is negative. So the rate of change was decreasing. So here the rate of change is increasing, okay, from here over. So we're going to use that to answer our question and say, okay, that means that from t greater than or equal to, and I'll just write it like this, 14/3, up to our endpoint of 12, which is 5 hours away, we know that the temperature is increasing at a faster and faster rate. C is increasing at an increasing rate. Well, what's our justification there? How do we get full points on this? Okay, well, it's pretty simple to explain that the temperature is increasing. That's because the first derivative of temperature of Celsius of T was positive. To show that it's not only increasing but increasing faster and faster, we show the second derivative is positive. So I'm a little short on room, but I'm going to try and write that down. I'm going to try and put that down for us, because C prime of t is positive. That's the first requirement. That means that C is increasing. And C double prime is positive. That tells me that the rate of change was increasing because the second derivative was increasing. Graphically, it would mean that the graph was concave up and increasing. It would look something like that. Okay, with what is the absolute maximum temperature from 7 to 12? Okay, to use absolute maximums, we need to have a closed interval. We do, from 7 to 12. All right, great. We just simply need to evaluate all the critical numbers and all the endpoints to find which one is correct. We already found the critical numbers of C. That's what makes C prime equal to 0. Or undefined, but there's no places to make it undefined. C prime is equal to 0 at, let's see, they were at 2. Okay, and another one at 14/3. Now we do not expect 14/3 to be a maximum because if you look at the sign chart we did earlier, at 14/3 we're actually at a relative minimum because we switched from going down to going back up. So possibly 2 or maybe the endpoint. So we just simply need to evaluate C at each one of these values. Now the time 7 a.m. is actually C of 0. Because that's when t equals 0, 7 a.m. Well, that is 27, I think. Oh, it's not at all, actually. Because we have to plug it into this original equation up here, which was t minus 3. So that's negative 3 cubed is a negative 27. That's actually 0. It's actually 0. Okay, so we'll make that 0. All right. Okay, so next we're going to look at C of 2. Okay, so C of 2 would give me a negative 1 cubed is a negative 1, minus 4 is a negative 5, plus 2 is a negative 3, and then plus 27 is 24. And I'm not going to go ahead and go through plugging in 14/3. I'll leave that to you if you want to do that. It will be a fraction, but it won't be our maximum. And I'll just skip right to the endpoint of C of 5. That would give me 2. 5 minus 3 is 2. 2 cubed is 8. 8 minus 25 is negative 17. Plus 5 is negative 12. Plus 27 is, what's that, 15? I have to double check that work real quick. All right. Looks like it is indeed 15. Okay, we're going to do one more question about this. So this is just another question to get you thinking about situations and how they relate. Let's suppose that we had a function R. That's the rate of evaporation of the pool. And let's suppose it's a function of the pool's temperature. How could we express the rate of change in the rate of evaporation? So we're talking about rates of rates here. We've got a rate of evaporation, and it is dependent in some way of the pool's temperature. So I'm going to say that the rate of change, evaporation R, is a function of C of T. That's what that means. So how I'm going to describe this function, rate of change, as R prime times the middle times the derivative of the inside. And we found all of these different things. So we now know that the rate of change of the evaporation is R prime of the original function, which I'll just grab here. times the derivative of that function, which we said was 6 times t. Oh, that's t prime. Oh, no. Actually, that's the wrong function. That is t prime. The original function was t minus 3 cubed minus t squared plus t plus 27. Then we'll multiply that times the derivative, which is what I had earlier. There we go. And we have a function. Even though we don't know what r is, we can describe how it would relate to c of t.